The electrochemical performance of electric vehicle batteries is governed by anode structural integrity. Synthetic graphite is highly favored for its superior cycle life and fast charging capabilities. However, transforming amorphous carbon into a crystalline lattice requires heating precursor materials to over 3,000 degrees Celsius. This process, known as graphitization, is highly energy-intensive. As shown in the regional cost comparison, industrial electricity tariffs dictate the geography of anode manufacturing. In Inner Mongolia, cheap coal-fired power limits graphitization energy costs to just $160 per metric ton. In contrast, developers in the United States and Europe face power costs of $320 and $600 per metric ton, respectively. This creates a severe regional cost premium that renders non-subsidized Western projects uncompetitive. The economics of graphitization are highly sensitive to grid tariffs and furnace efficiency. A standard process efficiency of 4,000 kilowatt-hours per metric ton, every $10 increase in megawatt-hour rates adds $40 directly to the cash cost. Transitioning to state-of-the-art continuous systems can reduce energy consumption by 40%. Yet, even these efficiency gains cannot fully offset the structural disadvantage of high Western grid tariffs. The steep slope of legacy batch furnace lines illustrates why older Western facilities face immediate economic obsolescence. Without direct power subsidies, domestic projects cannot bridge the operational cost gap. This physical constraint creates a profound environmental paradox for the green energy transition. The high-performance synthetic graphite anodes required for Western electric vehicles are overwhelmingly manufactured using highly polluting coal-fired electricity. Global production capacity expanded from 370 kilotons in 2018 to an estimated 1,600 kilotons in 2024. China-based, coal-powered facilities accounted for over 78% of this growth. By 2026, China's coal-powered capacity is projected to reach 1,700 kilotons, emitting up to 37.4 million metric tons of carbon dioxide equivalent annually. Meanwhile, non-Chinese clean-powered capacity will reach only 160 kilotons. This leaves the Western supply chain deeply tethered to high-emission coal grids. This structural bottleneck is historically analogous to the early aluminum smelting industry. The Hall-Héroult process forced smelters to cluster exclusively around the earliest cheap hydroelectric sources, such as Niagara Falls and the rivers of Norway. Today, modern graphitization remains bound to regions that can offer uninterrupted, low-cost industrial power at scale.